everybody, lesson 3.8 is finding the derivatives of inverse functions. So the first thing that I want to do for the warm-up is just to refresh how do we find the inverse and get the idea of what inverse is back in our minds. So remember, inverse functions exist when the domains and ranges are flipped, right? So x's and y's change roles. So if we were to find the inverse of a function g of x, first I like to write it as y equals 3x squared plus 1. And then step 1 would be to replace or switch x and y. And finally, we would resolve for y. So y inverse is the square root of x minus 1 over 3. So I don't love writing it as y inverse because it does look like an exponent right now. What I want to see it as is g inverse of x. This doesn't look as much as an exponent because it's on a function notation rather than a variable. All right, so that is just refreshing on how do we find the inverse of something. Okay. What I want to do now is remind us how we verified inverse functions. Because if we can remember how we verified inverse functions, you first learned about this in Algebra 2, then that will actually allow us to prove the definition of the inverse derivative, which is going to be introduced in a few moments. Okay? So if you recall, we could verify that two functions are inverses of each other if we do the function composition, and if f of g of x equals x, as well as g of f of x equaling x. Essentially, that implies that the operations are all opposite and they end up canceling each other out. So this verifies inverse functions. So in this section, we're going to be told that we're starting off with inverses, right? If f and g are inverses. Okay. Well, then, therefore, we can make this statement, right? Right, we can say confidently that f of g of x equals x. Now let's say we want to derive both sides. So I'm using my prime mark to show that I'm deriving. The left-hand side, what rule do we have? We have our chain rule, we have a composition. So the derivative of the composition of the chain rule is f prime g times g prime. And on the right-hand side, we just have an x, so that would derive to a 1. Okay. So then if our objective here is to find the derivative of the inverse, where g is the inverse, I can isolate g prime. That's what we're trying to find. Well, that's what we will be trying to find in this lesson. So the derivative of g, the derivative of the inverse, is equal to 1 divided by f prime of g. This is where it comes from. Of course, the rule is about to be introduced in a moment, but this is what we're going to accept as our rule. But here's the proof. So derivative of the inverse, assuming that f is differentiable and 1-to-1 with the inverse g equaling f inverse of x, if b belongs to the domain of g and f prime of g of b does not equal 0, right, that won't cause a 0 in the denominator of this rule, then g prime of b exists. And here it is. So we just proved it in general with an x. This definition is just giving it at a specific value of b. Okay. So we're going to calculate here g prime, where g is the inverse of the function f of x, x to the fourth plus 10, on the domain x is greater than or equal to 0. Okay. Now I'm actually going to show it to you both ways, because this is an example where you actually can. And what I mean by both ways, I'm going to find the inverse of f. Okay, I'm going to calculate that. I'm able to because I'm able to isolate and move variables around. That's not always going to be the case, but that'll help us acknowledge that, okay, wow, this rule does really work. So I'm first going to say y equals x to the fourth plus 10. Then I'm going to say x equals y to the fourth plus 10. So x minus 10 equals y to the fourth. And I can apply a 1/4 power here. So y equals quantity x minus 10 to the 1/4 power. So that really is our g, right? So then if I want to find the derivative of this, it's a chain rule. So 1/4 is the outer, inner stays to the -3/4 now. The derivative of the inside would just be a 1. Okay, awesome. So that would be the straightforward way. Find the inverse's derivative. So I found the inverse and then I derived it. Can't always do that. If we're only given a function and we want to know the derivative of the inverse, sometimes we're just going to have to use the rule, like we see above. Okay, so then based on this rule, g prime of x would be equal to 1 over f prime of g. Okay, so I need to figure out what f prime is, and then I need to be able to plug g into it. Okay, so f prime, little side work here, is 4x cubed. So g prime of x would then be 1 divided by 4 parentheses. Okay, and g is going to go inside here. Okay, so let me... I was putting f in by accident. G we found on the left-hand side, and that is x minus 10 to the 1/4 power. Okay, so it doesn't look exactly the same, but if we move things around and simplify them, we have 1 over 4 x minus 10 to the 3/4, and if we wanted to, we could bump this x minus 10 to the 3/4 up and have a negative exponent. Okay, so you can see that we do get the same answer using equation number 1 versus start to finish. Now, this is an example that I would never use the inverse rule in this situation because I'm only given information about f. I'm actually able to solve for g, the inverse. I might as well just derive g. But this is a good one because we're able to show it side by side and prove that, of course, we're going to get the same answer. So this second example, calculating g prime without solving for g. We want to calculate g prime of 1, where g is the inverse of f. You have to be told that, right? We can't start this problem with the assumption that it's the inverse. We have to know that it's the inverse. So the first thing I always do, I kind of think of these problems as a puzzle. So I always write out what I need. So if I want g prime of 1, based on the rule, I know that I need 1 over f prime of g of 1. Okay, so that's what I'm looking for. F of x is given. I'm going to need f prime of x. So I do that as side work. F prime of x is 1 plus e to the x. The next thing I need is g of 1. But I kind of pause here and I say, well, I don't even know what g is. How can I come up with g of 1? Okay. So here's where the fact that they are inverses comes into play, right? And by definition of inverses, domains and ranges change roles. X's and Y's switch. So we can use the fact that g of 1 equals some question mark, and since f and g are inverses, then f of that same question mark has to equal 1. Those two go hand in hand together. So that's the piece of the puzzle that I need to work backwards and figure out what g of 1 is equal to. So f of what would give me 1? So x plus e to the x equals 1. When does this happen? So it's not always something that you can easily solve for. Usually it's like a guessing and checking game. The values are going to be pretty easy to work with, though, so you're not going to think of some crazy decimal answer. It's going to come up to be a nice, easy value to find. So it can't be 1, right, because then that would be 1 plus e. That's larger than 1. Negative 1 wouldn't work because that would give me a decimal answer. So x equaling 0 is the value that I'm looking for, because I would have 0 plus e to the 0. Anything raised to the 0 is a value of 1. So the missing number that I was looking for is 0. So now I have the pieces of the puzzle that I need. I have my g prime and I have my g of 1. So g prime of 1 is then equal to 1 over f prime of 0. We found what f prime of x is, so our final step is to plug 0 into f prime. So we have 1 plus e to the 0, or 1 plus 1, and we get a half. So the fact that they are inverses allows us to solve for that missing value of g of 1 here. Okay, you try. So find g prime of b when f and g are inverse functions. F of x is equal to 4x cubed minus 2x, and b is negative 2. I'm just going to pause for a minute so you can pause your video and try to work through this on your own. I'm going to work through silently. So you should come to an answer of 1/10. The x value that we were looking for when f of something equals negative 2 was negative 1. Through guess and check, if you really get stuck, you could take 4x cubed minus 2x, add the 2 to the left, set equal to 0, and graph it. And then the x-intercept would be the solution that you're looking for. Okay, try to avoid that because we want to try to do this without calculators, but that would be the easiest way to solve it if you really got stuck. Let f of x equal x to the 5th plus x cubed plus 2x. G is the inverse of f. Using the formula, calculate g prime of 4. Same problem here. I'm going to leave this one for you to work through on your own, and then we'll compare answers in class. Okay. Skip this for now. So if we want to derive cosine inverse, right, then I'm going to say my original function was cos, and my inverse function, of course, is cos inverse. So if I want to get g prime, then I'm going to use 1 over f prime of g. Okay. So side work f prime is negative sine. So g prime is 1 over negative sine of cos inverse of x. Okay, so if we keep thinking about this, trying to simplify it, right, what does cos inverse of x mean? Well, let's get our right triangle trig going. We call this theta, right? We're really looking for an angle measurement when we're doing an inverse trig. Okay, so cosine is adjacent over hypotenuse, so we have an x over a 1 in this scenario. Okay, so theta is theta, right? So in this case, cos inverse of x based on my drawing is just theta. But what is negative sine of theta? I don't want my answer to be in terms of theta because my derivative is in terms of an x. So I have to keep going. What is negative sine theta? Well, sine of this angle is opposite over hypotenuse. So what's my opposite side? Well, I can use Pythagorean theorem. So 1 squared equals, I'll call this b for right now. 1 squared equals x squared plus b squared. Right, so if I move this around, b is equal to the square root of 1 minus x squared. So then negative sine theta, this comes out to be, I'll put the negative up top instead. Negative 1 over square root of 1 minus x squared. So that would be the long approach for solving all of these, and that's where the rules that I had just shown you before, that's where these all come from. Okay? This one was done without a chain rule. So this section gets particularly harder when x is not just x, when we have a chain rule inside of an inverse. So I'm going to talk us through that next. And let's go here. Okay, finding the derivatives of inverse functions with trig. So these are things that you'll have to memorize if you are in the AB or the BC class. If you're in the regular class, you won't have to memorize these. So the derivative of sine inverse is equal to 1 over square root 1 minus x squared. Tan inverse, 1 over x squared plus 1, and so forth. So take a moment, get these jotted down, and then we're going to talk about them in conjunction with the chain rule. I'm going to actually go back to the problem that I crossed off and approach it without using this trig inverse to help us prove this perhaps. Okay, so back to these rules with respect to x. Now, if x was not just x and it was u, I'll use u anytime we're talking about something other than x. Here's what the change would look like. If this x were a u, right, that top number 1 really came from the very first slide when we derived the composition equaling x if we have inverses. And if I derived that original x on the right-hand side, it went to a 1. So that's where these numerators of 1s are coming from in all the problems that we've been doing. So if it starts as something other than x, it starts with 2x or 10x or x squared, whatever it is, then the derivative of that is going to find itself up top, u prime. And this x is going to turn into a u. Okay? So that would be true for every other rule here as well. So if you have a chain rule inside of a trig inverse, you can think of it as a u. The numerator becomes a u prime, the other x's become u's. Okay? Now I'm going to also, at the bottom of this page, show the chain rule inside of inverses. Okay, what I was kind of referring to just before. So if we have, if we have f of g of h, of x, of course, and we are told that f and g are inverses. H is just an additional term inside of it, an additional input. Okay. Then if they are truly inverses, just like before where the inverses kind of simplified and ended up equaling x, well now it would simplify and equal h of x. So if I wanted to derive my inverse functions, and I derive both sides here, okay, then I would get f prime of g of h times g prime of h. Equaling h prime. Right. So I'm not completely finishing out the chain rule on the left-hand side, and I'm doing that on purpose because I'm looking to find the derivative of g. So g prime of h of x, that's still in there, is equal to what we have over here. Okay. So then if I solve for g prime of h of x, it is equal to h prime divided by f prime of g. Okay. That's what happens up top where I chose to put my u's. The u's are like the h's in this example. Okay. All right, so let's look at our first example using the rules. We can prove it as well, but we're going to use the rules. So we want to find f prime of x, f prime of 1/2, where f of x is equal to arc sine of x squared. So arc sine is also written as sine inverse of x squared. That is our f. Okay, which means our g, which is kind of reversing the rules. I don't like when they notate it this way, but anyways, the g, the original, is sine of x squared. Okay. So by the rule, if we want to find the derivative of sine inverse of x squared, or sine inverse of u, then we are going to use u prime divided by square root of 1 minus u squared. So we can literally just input, once we have these rules memorized, u prime is 2x, square root of 1 minus x squared squared is x to the 4th. Okay. So we're done there with the derivative as a function. We want the derivative at 1/2. So 2 times 1/2, square root 1 minus 1/2 to the 4th power. So working through this, I would have 1 over square root 1 minus a 16th, or 16/16 minus 1/16, so 1 over square root of 15/16. We might as well simplify this a little bit, right? If we're dividing by that fraction, plus the square root of 16 can be simplified. So this would flip and come out to be 4 over root 15. Okay, so that's using the rule. If you want to see this using the proof, I think I have enough room here to work on it. Okay, if you want to see it using the proof, so again, f of x equals sine of x squared g of x, I'm labeling it differently right now. I'm sorry. G of x equals sine inverse of x squared. Let me reverse that so that I'm consistent with the original problem. So g of x is sine of x squared, and f of x is sine inverse, based on how it was defined originally. Okay, so if we were to derive the g, right, that goes to cosine of x squared times 2x. Okay. Then we know that we would need 1 over cosine of g of h of x, so cosine of sine inverse of x squared times that 2x. Okay. So now I'm going to take this and put it on my triangle. Here's my theta. Sine is opposite over hypotenuse, so I have an x squared, and I have a 1. then I need to figure out what this a is. So I have 1 squared equals x squared squared plus a squared. So a equals square root of 1 minus x to the fourth. Okay, so then if I want cosine of that, then I take a over 1. Oops. So this first became okay, last example for this lesson. So we're looking at cosecant inverse. I'm not going to prove it this time. I'm just going to take the rule. Cosecant inverse of e to the x plus 1 when x is 0. And we're using the rule negative u prime divided by absolute value u times the square root u squared minus 1. Okay, our u in this case is e to the x plus 1. So our u prime would be e to the x. We have a negative e to the x divide by absolute value e to the x plus 1 square root of e to the x plus 1 quantity squared minus 1. And now we just replace the x's with 0. So negative e to the 0, e to the 0 plus 1, e to the 0 plus 1 squared minus 1. Simplifying that, we would have negative 1 divided by 2 times the square root of 3 as our final answer.